when we observe the dowel with a washer on the end bobbing up and down in the water, we first attempted to measure the restoring force constant by adding a 0.2 gram weight on top of the dowel. Now the top of this 0.2 gram weight doesn't line up with the top here. But what happens is we have x equals 0 at this altitude, or at this position. The addition of the 0.2 gram weight caused the system to sink 0.0125 meters, 1.25 centimeters or 12.5 millimeters deeper into the water. That was about this much deeper from just the addition of 0.2 of a gram. We note then that the system must have been exerting a restoring force of 0.002 newtons trying to get back here. 0.002 newtons being the weight of the 0.2 gram weight, the 0.2 gram mass. When the system sunk down, we got an increased restoring force, allowing the system to come to equilibrium here, and the increase in the restoring force, or the increase in the buoyant force, I'm sorry, we got an increased buoyant force tending to restore the thing back toward equilibrium, which supported the 0.2 gram mass, or the 0.002 newton weight. Okay, so we had a restoring force there from the buoyancy of 0.002 newtons. The buoyant force in this case we'd say is equal to the, well, in this case we say the buoyant force is equal to the weight. In this case the buoyant force would be equal to the weight plus the 0.002 newtons. In each case the buoyant force supplies the force that's the equilibrium force necessary to hold the system in equilibrium. Now this is the equilibrium position of the system without the mass, and this will be our equilibrium position for our simple harmonic motion. From our observation that a force of about 0.002 newtons was associated with a change in x of negative 0.0125 meters, we get k equals negative f over x, comes out about 0.157 newtons per meter. Turns out that this is about half of what it really should be, and I'm not sure how we managed to miss it by a factor of 2, but we did. Now, given that measured force constant and the mass of the dowel in the washer, which we determined to be 0.0055 kilograms, we were able to predict the omega for the system, the angular frequency, square root of k over m, came out to be 5.3 radians per second, which predicted a period of about 1.2 seconds. That's not what we measured. We measured a period that was closer to 0.7 seconds than to 1.2 seconds. So we missed it by a mile, or at least by half a second. Let's analyze the situation theoretically. If we have the system in the water, and if we sink it by distance delta x, if we push it down by distance delta x, so that this volume gets submerged, then we're going to have an extra buoyant force that's equal to the weight of the water displaced by this volume. In other words, equal to the weight of the water that would fill this much volume. Now the diameter of this dowel is 1/4 inch, 6.35 millimeters. So the volume of the length delta x is of course going to be its cross-sectional area times delta x. That's going to be our delta v when we push this thing down. Remember that this delta v will tell us how much water gets displaced, which will tell us how much buoyant force we have. And we easily calculate delta v from the radius of this thing. The diameter was 6.35 millimeters, so the radius is 3.18 millimeters. And we get a volume of 31 square millimeters, which is the cross-sectional area of this thing, times delta x. Now a square millimeter, did I say 3.1? It's 31 square millimeters. In any case, It takes 10,000 square, a million, I'm sorry, square millimeters to make a square meter. And when we do a conversion, we see that this is 3.1 times 10 to the negative fifth square meters times delta x. Now how much would the water displaced by this volume weigh? Because that's going to be our buoyant force. Well, the weight of that water is going to be negative delta m times g, where delta m is the mass of the water displaced. The mass of the water displaced is going to be the volume, 3.1 times 10 to the negative fifth square meters times delta x, multiplied by the density of water, 1,000 kilograms per cubic meter, to get the mass of the water displaced, and that times the acceleration of gravity. From this we see that the delta F corresponding to the displacement delta x is negative rho delta VG. Rho is your density of water, delta V is the volume. And we get all this, as we saw before. And this comes out to negative 0.294 newtons per meter times delta x. Now, if F equals negative K delta x, then right there's our K. So here is K for this system, negative 0.294 newtons per meter. Omega then is square root of K over m. Putting the K and the mass of the system in, we get 9.2 radians per second, which gives us a period of 0.67 seconds, which is almost exactly what we observed. So the theoretical calculation, based on the buoyancy of water, Archimedes' principle and so forth, comes out just right. Let me point out that this reads, row, row, row your boat. If you're reading nursery rhymes to a bunch of kids, you don't want to misread a row as a P. Think about that for a minute and make sure you understand how row differs from P.